Hello everybody and welcome again to your channel Thermal Engineering Concept and the Principle. In a series of episodes, we are going to introduce the concept of condensation and how to deal with it, whether it was a condensation process over or inside vertical and horizontal tubes. How can we estimate the heat transfer coefficient for condensation of fluids as they pass over the outer surface of tubes? Let us go through the details of this episode. Welcome, my friends and colleagues and followers. The condensation process is one of the important topics present in modern industrial applications in the field of energy and heat transfer. We may find the condensation process in many topics and fields of industry, such as petrochemical factories, refineries, food industry, power plants, air conditioning and refrigeration, and many other topics that is experienced in the field of thermal engineering. The prediction of condensation process and the performance of a heat exchanger is mainly based on the heat transfer coefficient and how accurate it has been predicted. Condensation can occur in different orientations: vertical, horizontal, single, or tube bundle. And in the present episode and the following episodes and videos, I will introduce the condensation process in different categories, whether it was external or internal flow. Thank you for your support and continuous assistance that is afforded by your side to the channel, and let us go directly to the objectives of the present episode. The objectives of the present episode are available correlations which can be found in the open literature. Some of them will be mentioned here in this video, and then we will take a practical case study for condensation of vapor on horizontal tube bank by using some of the mentioned correlations. And finally, we will arrive to the closure of the content of the present video. There are quite a good number of these correlations which can be used to predict the condensation heat transfer coefficient over tube bank. In this table, I will mention some of them. Maybe Jacob in 1949 based his correlation on the single tube condensation on horizontal tube presented by Nusselt in 1916 by adding the effect of the condensation which passes from one row to another, uh, and that will reduce the overall heat transfer coefficient, of course, because the condensate will cover more surface area, and then it will add um, a resistance to the condensation process at the surface of the rose after the second. And then when you go to the third, it will be more difficult as well, and the heat transfer coefficient will be less, and so on. So he has added uh, um, a sort of correction to the single tube condensation by using equation 1b, where n sub r represents the number of tube in a vertical column to the power minus quarter. And then Kern presented the equation which is based again on Nusselt equation by using nr to power minus 1 over 6. And he said that the presentation of Jacob with equation 1b, it is really a conservative and will predict low heat transfer coefficient, which requires or overestimate the surface area of the condenser. Planck in 1978 suggested multiplying the single tube coefficient as presented in equation 1a by Nusselt by a factor of 0.7, and using nr to power minus quarter is similar to that of Jacob. And this suggestion was based on experience and uh, practical experimental data available for condensation process. And finally, Tarad in 1997, again, he has based his equation on Nusselt equation 1a, and nr is raised to the power minus 1 over 5. And this suggestion was based on the assumption or fitting of the available experimental data as collected from steam condensers in power plant. And it gave about 95% of the data lied on this uh, line of correlation. These equations, and you may find more of these correlations. I will put some references in the link uh, seated in the description box below this video. Practical case study. Let us consider a condenser, which is a part of organic Rankine cycle that circulates R123, and this unit or this cycle uses uh, waste energy recovery system from the site where it has been used. We need to estimate the heat transfer coefficient for the bundle shown in figure 2, where we have horizontal tubes, 44 horizontal tube arranged in two passes as shown in this figure. The tube is made of copper with a diameter external outside 12.7 and internal 11.07 with a tube length of 2.24 meter long. And we have a refrigerant flow rate of 624.5 kilogram per hour, where the vapor enters the condenser as saturated vapor at pressure 1.31 and to be condensed on this tube bundle. Of course, the table 2 shows the uh, thermal properties, physical properties, starting from saturation temperature of 35, and we have the liquid viscosity at the bottom row as 0.372 times 10 to power minus 3 Pascal second. And we will use these thermal properties in the solution of our example. The solution for this case study, we start with calculating the condensate tube loading gamma sub HO horizontal equal to m dot refrigerant divided by L sub P, the length of the tube, and times the number of tubes. The result will be 0.176 times 10 to power minus 2 kilogram per meter second. And the number of tubes in a vertical row represents a mean value that corresponds to 2/3 of the number of tubes in the central row as mentioned by Kern. And then we will get an R two-third times 8, then 5 tubes, the value of an R to be used in calculating of heat transfer coefficient. Let us start with Jacob. Jacob HP mean value equal H1 times N sub R to power minus quarter. We have H1, it means the heat transfer coefficient at the first tube at the top row. If we substitute the values of the thermal properties, then we will get H1 2194.44 watt per meter square Kelvin, and H sub B as a mean value will be 1467.5 watt per meter square Kelvin. Then Kern correlation is the same value for H1 times an R to power minus 1 over 6. Then we have H1 is equal to 2194.44 watt per meter square Kelvin, and H sub B as a mean value is equal to 1678.1 watt per meter square Kelvin. Of course, here we have an R to power minus 1 over 6. Then Frank correlation in 1978, we have an R to power minus quarter, and we should multiply H1 as the coefficient 0.95 by 0.7 to be 0.665, and then we will get H1 0.665 times KL times the bracket to power 1/3, then it will be 1536.11 watt per meter square Kelvin, and H sub B as a mean value is equal to 1027.3 watt per meter square Kelvin, and here we have an R to power quarter as well. Let us use Tarrant correlation as well. 1997, we have an R here is to power minus 1 divided by 5 or 1/5. Then H1 is the same as that of equation 1a, and that will be 2194.44 watt per meter square Kelvin, and then we have an R is raised to power 1/5. Then the result will be 1590.5 watt per meter square Kelvin. Tarrant correlation can be used as mentioned in this in the table of this episode, but with the use of one of the correlations of the single tube, which has been presented in the previous episodes, that H1 equal 1.05 instead of 0.95 or 0.665 as mentioned by other published correlations. Then I will use this correlation with the use of that. Then the heat transfer coefficient of the tube at the top row will be 2425.43 watt per meter square Kelvin, and applying the correlation as shown by raising the NR to power 1/5, then the heat transfer coefficient will be 1758 watt per meter square Kelvin. With a brief, then we will see the heat transfer coefficient for different correlations and authors. We may find that the lower value was predicted by Frank, and we have Jacob, then we have Tarad 1997, followed by Kern in 1958, which is equal to 1678.1, and the highest value was predicted by Tarad 2022. That is a value corresponds to 1758. And the choice of any of these correlations, of course, will depend on what we have in the practical case, which we are going to use. Most of these are depending on the analytical solution presented by Nusselt, and then each of these correlations includes just the number of tubes at the central column to a power. Dear friends, now we arrive to the closure of the content of the present episode. We talked about the available correlations to predict the heat transfer coefficient for the condensation process over a horizontal tube bank, and the practical case study for the condensation of vapor in a condenser, which is used as a part of organic Rankine cycle. And we predicted the overall heat transfer coefficient by different correlations. Of course, we have some valuable resources can be found in a link seated in the description box below this video. You may make use or advantage of these references. And if you feel that the content of the present video are useful to you and others, please subscribe and share it. And don't forget to leave your like at the bottom of the video, and see you in the near future for other uh, uh, processes in the condensation topic. Bye bye.